And okay, can everyone see that?
Yes.
Okay, so I'm now going to give an interpretation for a logic for Q categories. So we've kind of been building up to this. This is actually not the final form, and I'll explain a little bit why in a bit. But the idea is we want to we're trying to create a good explanation of the container side of OSLF. So OSLF says that the meaning of a formula is going to be a container, like a set or a list or a graph or whatever, of all the formulae, of all the programs that give witness to the truth of the formula, or to the truth is not quite the right word, but bear witness to the formula. And so sets are very interesting, very easy to do. Christian Williams created a nice categorical account of that idea. But what he didn't do was to show how to vary the container. So we're focusing right now on just one other kind of container, and this container we're using Q categories because if we use a Quantile, then the logical operations that we get will correspond to linear logic. And we can see that here in the logic. So these are the constants in linear logic: top, bottom, 1, and 0. And these are the logical operations. So linear negation, tensor, with, par, and plus. So those are the linear operations, and we inherit them directly from the Quantile. These are interesting. They have required a lot of care to get right. And then these, this in particular comes from the fact that this is a Q category. So the Q category is a pair where you've got an underlying set, which we will denote with the vertical bars around X, and a relation, which we will denote with X of big X of little x1 and little x2. But this relation is not just true or false. So it's not just that x1 is x related to x2 is either going to be true or false. It's going to take a value in Q. So if it's absolutely for certain, that would be top. If it's decidedly not, that would be bottom. But then there are a whole range of values in between top and bottom that are given by the Quantile. So an example of a Quantile would be like these tropical, so-called tropical mathematics. So max plus, where max is interpreting the join here, and plus is interpreting the tensor. So if you took like the integers under max plus, that would be an example. So X, the underlying set X would be the integers. And the relations are given in terms of, well, the underlying set could be anything actually. Just we want to interpret them in terms of the max plus relationship by giving a map from X to the integers. So if you took the integers as the basic thing, then then you would get this relation as less than or equal to for the integers, and then these operations would be max and plus, and then everything else follows. Negation would be minus, if I get that, if I recall correctly. So that's an example. So the main thing that we have to do is to give an interpretation of this. So this is going to be interpreted in terms of that. And then we introduce variables. So you can have a variable on the right, a variable on the left, or a variable in both positions. And these variables range over X. But then you could also substitute in a variable here in any of these positions. But that variable ranges over values in Q. So if you think about it, then an interpretation of a formula phi is going to take two additional parameters, not just phi, but an environment for the X variables and an environment for the Q variables. So this, which will range over with E is going to say how to interpret your X's, and H is going to say how to interpret your Q valued variables. So then the interpretation is quite straightforward with no surprises. So the interpretation of the formula top is just the top of the quantile. The interpretation of the formula bottom is just the bottom of the quantile, and so on for the constants. The interpretation, as we said, of the less than or equal to relation here is just the X relation, which is given in terms of the Q category. And then when you introduce variables, well, if you're using the X valued variables, you need to run the E environment to go and get the X value in X, and then you run X of that either on the right or the left. And then similarly, if you have variables on both sides, then you use the E to go and get X values, and then you run X on that. Likewise, if you have a Q valued variable, then you're going to run H on the Q valued variable. Then the negation is just the negation that you have on the quantile. So we're assuming specific kinds of quantiles. So there are quantiles where you don't have negation, but we're assuming a quantile that does support a quantile-like negation. And then the operations, just like with negation, the operations push through, right? So for any of these operations here, we just push the interpretation across the operation. So the operation becomes an operation in the quantile. And then Mike and I spent a lot of time on this. There is a categorical version of the quantifiers, but it doesn't fit with this type judgment for the interpretation, which raises a bunch of interesting questions. But at a minimum, we can give a nice and natural interpretation. So we're going to have to think about, like algorithmically, why is this one picked out, right? So I wrote this down because it's obvious and natural. But a computer is not going to make a judgment like this is obvious and natural. So we have to say why algorithmically this is the only choice. So and I'll talk a little bit more about that in just a second. But essentially, in order to understand this, note that if you have a function that goes from, if you've got two Q categories, say C and D, and a Q functor from C to D, then the Q functor, say F, is a map from the underlying set of your Q category C, which let's say is X, and maybe it's easier if I call them X and Y and abuse notation that way. So a Q functor is going to be given in terms of a map from the underlying set of X to the underlying set of Y, which preserves, which is bounded above by the relation. So F of whatever the value is that is given by X of X1, X2 has got to be less than or equal to Y of F of X1, F of X2. Hopefully that's clear. If it's not clear, I can write it down for folks. So anyway, but notice that if we have an F that's just, if we just think about what's on the underlying sets, there's a unique lifting of that F to predicates. And basically it doesn't do anything to the constants. It pushes through on the operations. It applies F to the left-hand side and the right-hand side of less than or equal to judgment, which is, precisely what we need for the for functoriality. So that's where we're assuming that F is a functor, and then it does all the right things for variables. So that's kind of the basic idea for this F psi construction. So if we have a for all F psi, then I'm going to apply F psi to psi, and so that carries me over into the Y Q category, and then I'm going to interpret the formula, that new formula, but I'm going to take the meat of all of the possible interpretations given all of the environments that I construct from Y variables to Y. And then for the there exists, it's a join instead of a meet. So this is least upper bound, and this is greatest lower bound. Sorry, no, it's the other way around. Greatest lower bound, least upper bound. Yeah, greatest lower bound, least upper bound. So this one will be the smallest thing that dominates all of these, and this will be the greatest thing that's less than all of these in the quantile, right? So these are all going to give me Q values, and I'm going to take the meet over all those Q values, and here I'll take the join over all those Q values. So that's it. That gives us a very interesting logic. It's at least as rich as the logic of quantiles. You can think of it as a kind of relaxation of the logic of quantiles, because we have these sets over here that are being where there's this relationship amongst the elements that's being mapped into the quantiles. So that's there are different ways to think about that, but it's at least as rich as the quantile, and we know that the complexity of linear formulae is through the roof. So this is an incredibly expressive logic. Any questions so far?
I'm curious about the roadmap of OSLF now that you're kind of working through, defining and working through the mathematics of the container. With OSLF, how far along are you? You think you're 50% of the way there? Are you 80%? Are you still at 40?
We're I mean, in terms of having a useful formalization that can be reduced to code, we're 100% of the way there, as long as your containers are only sets. So there's a full and complete specification that can be reduced to code using Christian Williams formalization. So if, however, you want to vary your containers, then let's say we're about 50% of the way there. So if you take a weighted average of the two, right, you could say, I don't know, we're something like 3/4 of the way to the point where we can reduce everything to code.
So that aspect of being able to vary the containers in my mind, that seems like that's a pretty heavy lift to be able to account for all possibilities. Is it, like the last 20% of the possible variations? Is that, do you see this as achievable in the next 5 years? The getting
Oh,
all the
easy, easy, no problem. Yeah,
okay.
varying the contain, yeah, because um, I mean, varying the containers is not at all important if we want to just generate basic type systems for any programming language.
Okay.
If we want to generate query languages, we can leave sets as they are, but if you want update in your query language, where the semantics is not ad hoc, then you need to be able to vary the containers so that you have a notion of update. And that's essentially why I'm focused mostly on the linear stuff. With the linear stuff, we can concoct a notion of update, and then and that will solve the rest of the query language semantics. And then from there, things get, you can get as wild and crazy as you want, but we can leave that to future researchers. I'm mostly interested in type systems and query languages. And then I'm also interested in what this says about the foundations of computing and mathematics. So,
Can I ask you?
hopefully that makes sense. Yeah, go ahead.
I'm thinking about what you explained about for all and exists, and so in with a set we have elements, and we can ask, is this element exist in the set, or so? But you said that
no, that's not what this is saying. That's not what this is saying. So this is saying something pretty different than that. So here, if we imagine that phi, sorry, C is a quantifier free itself, right? So this is the first time we've seen a quantifier. C may be very complicated in terms of these operations, but there's no inner quantifier, right? So then this thing is taking as input that logical expression together with some f, right? And the f is going to tell you how to carry x's over to y's, right? So we were living in an x q category, and we're going to move over to a y q category. And so then we know how to apply f to c according to these rules. So that'll allow me to interpret this thing over in Y land. Okay, but that may still have some variables in it, right? So there may be, we've converted X variables to Y variables. So we need to now give a binding for those Y variables. And essentially what we're saying here is that this thing binds all of the Y variables. So, I mean, I can make it so that you list them out and you only say which ones you bind. But if we want this thing to be closed without additional, mention of variables here, then what you're doing is over all the environments mapping Y variables to Y values, we're gonna do a big giant meet. Does that make sense?
I'm struggling to understand the variables in this context. What exactly do you mean?
So here, these are constants, right? They come from X. But here, this is a variable. We're saying there, you could say there is a variable such that there is an X, which is bigger than this specific X. right?
Bigger in a sense.
In the sense of the X relation. So X
I see.
tells, right? And so, and then, so there are lots of maps which take, you know, V to an X in X, right? Now, what we want to, so, I mean, we know how to interpret, if you give me a particular map, so a particular environment, then I can interpret a statement like this, right? Your particular environment is going to tell me how to bind this. So let's say it is bound to X prime. Then we know precisely what to do here. We're going to run the X relation on X, which is, you know, the given value here. And we're going to look up the variable V, but E says that V is bound to X prime. So now I have an X and an X prime, and I feed that into the X relation, and that's going to give me a Q value. Right? And so if you think about it, so mathematics currently sees in black and white, right? It sees in true and false. So that's the kind of color vision that math has. And what Q categories do is they say, you know what? There's a big wide color space, and we're going to let you see in color instead of black and white. And so the Q values are the colors. And so when you compare two things, you're going to get a color back, right? These are specific colors, right? This is all colors, white. This is no colors, black. So in a additive color map. I'm not going to talk about these, but you know, they're somewhere in the middle. Call them, you know, brown. These are various shades of brown. And so now we know how to combine colors, right? So this tells me one way to combine colors. And so if you were thinking, if the colors were frequency numbers and you were using max plus, then this would be adding the frequencies. Whereas this would be taking the maximum of the two frequencies. Right, so that's one way to think about it. So in general, phi is going to be interpreted as you give me a formula, but you also have to give me two other things. You have to say how to map whenever I hit a variable. You have to tell me what the binding for that variable is for the X side of things. And if I hit go ahead.
This is like some kind of environment where we have these variables.
That's correct. Yeah, this is an environment, which is why it's called E.
Oh, okay.
Right. So E for environment tells us how to resolve X variables. So these things range over X's. And H is another kind of environment, and that tells me how to resolve Q variables. So here I can also, in the same way that I can have formulae here in my spec, I can also have variables. So these stand for Q values. These things stand for X values. When I plug them into a relationship thing, that will give me a Q value back once I have a binding. And these things just stand straight up for Q values. So if you think about it, another way to think about it is there are two kinds of contexts, right? So all of these, I could poke a hole in everything here by replacing C with a hole. And so the Q valued variables are holes for these things. So this is like a multi-hold context. And over here, there's a different kind of thing, because while these are all Q values, anything in the relationship part from here to here, those can only take X's, right? So these are X contexts, and these are, poking holes in these relationship things. So that's yeah, right. So then to interpret one of these, and then what this does is it basically closes up over this. Now it occurs to me that I should not only close up over this, but I also need to close up potentially over the H's. So it's useful to have this conversation because I'm now seeing that there's another opportunity here, which is to close up over the H's. So I will think about that. But that's basically the idea, is that we're using the quantifiers to close up the holes where there are variables. These are binders, basically.
Yeah, this is what I wanted to ask. You're saying that now we can express not only true false, but anything what we want, and this comes
not
from
anything. No, not anything.
I mean,
it's really important that Q is a quantile.
Yeah, this is what I want to ask. This comes from the Q category.
Yes. Yeah. So this is what I've been saying all along, is like, so you get and or over in set valued land because you have this natural interpretation on sets for intersection and union. Right? So there's an algebra on sets that corresponds to your logical operations. Likewise, there's an algebra on quantiles that correspond to your linear operations. Right. So we can think about this as a very primitive linear data structure.
And this is not part of, so we have environment of the X values and Q values. And the relation, do we have a relation already in this environment when we have the variables? Or
this relationship here is going to interpret this relationship here. So this,
oh, I see.
Yeah. So because I've talked about it so many times before, I didn't put all the stuff here, but a Q category comes with some specific data. It comes with an underlying set, which we denote, absolute value of X, and a relation, which we just reuse X to denote that relation. In the standard literature, they name the relation separately, but it doesn't make sense. I mean, you can be a little more parsimonious and just use X to name the relationship, but this relation is not truth valued, it's Q valued. So given a little x1 and a little x2, I can say, when I apply the relation X to those two, what I get is a value in Q, which is a quantile. Right?
I see.
So Q is a quantile. I'm going to pick, Q gives me all my colors and how I can combine, how I can mix colors. And this tells me what the color is between these two. And so this thing is mapping to that thing. So naturally, that's what this says, right? That's exactly what this line says.
Yeah, I see. So what we get from x1 less than x2, this is exactly the Q value that is, or this relation in X.
Yes,
directly. We are picking this relation.
Yes, correct.
Oh, I see. Yeah. And we can, when we have this less than expressions, we can combine them with linear logic operators.
Bingo.
Together. And
bingo. Yes.
And we can produce another. We're just combining and get the bigger expression, well,
not necessarily the bigger one. It depends, right? This will be the greatest lower bound. This will be the least upper bound.
or just normal and or we can apply them
No,
too.
sorry, those don't live here.
Oh, okay, okay. Mhm.
If you want normal and or, don't use Q categories.
Mhm, mhm. And I also wanted to ask you, what is the difference between a Q category and topos, and why?
Yeah, so this is precisely the point. The topos is very, very set like, even though it, you know, there are things that are toposes that are not sets. Topos really captures the essential quality of set. So you'll get and or and for all, and there exists, and you know, the sub-object classifiers and blah blah blah. So it's not going to be linear. That's the important point. It will not capture linear logic. You can code linear logic in a topos, but that's not the same as a direct interpretation.
Mhm. And if we want to go from here to topos, we can do that.
You can build a topos on top of this. So there are two different ways. So this is what I've been trying to say for a long time now, which is that sets have this property, and it's really at the heart of what blockchain does for us. Sets make it super easy to copy things. So sets are like the current internet, where if I make an electronic document, I can make a copy and send it to you, and you have a copy of the document and I have a copy of the document. Just like what everybody does on Facebook today. I make a photo of my dog, I put the photo up on Facebook, someone loves that photo and they download it on their machine. Now there are two copies of that photo. And what blockchain does is says, hey, wait a minute. If that photo were like an orange, if I gave you the orange, I don't have the orange anymore. So copying is not something we can do. If we want it to be like an orange, then we have to prevent the copying. Or more reasonably, we have to say how to implement copying in terms of lower level, more primitive operations. Does that make sense?
Yes, yes.
Okay, right. So, and if you get down to brass tacks, if we believe in quantum mechanics, which is a big if, you know, like we know quantum mechanics is wrong. We know general relativity is wrong. there's something that supersedes them for sure. We know that. But currently quantum mechanics is our best guess to like 30 decimal places of accuracy as to how things function in the physical world. So if you wanted your math to be grounded in physical reality, then the foundations shouldn't be set. Now, it's a big if. Maybe you don't want your math to be grounded in physical reality, right? Maybe you like math that's grounded in a more digital, easy to copy world. But if you happen to really want your math to be directly connected to physical reality, then you'd want your math to have a foundation that's more linear. Does that make sense?
Yes, yes.
Okay, cool. So these are motivations for why we might consider linear as the floor. So you can go from set to linear in this, from topos to some linear construction like a Q category or something else, by coding up how set, you know, how the set operations would be interpreted in a linear world. And in fact, that's the basis of Girard's interpretation of classical or intuitionistic logic. So what Girard says is, I've got to have this bang operator, which tells me how I get to make copies. And then I'm going to interpret the intuitionistic implication. So this is ordinary lambda expressions, right? Intuitionistic interpretate the intuitionistic arrow, the implication is the type for a lambda expression, right? A function in Scala. and I'm going to decompose that into bang x. So now I'm allowed to copy lollipop. So that's the linear implication where I only get to use things once to y. So the point of that interpretation is it's telling you how intuitionistic topos-like computations are encoded in the linear world. That's the heart of the interpretation. And so it makes sense to think about layering a digital universe where copying is easy on top of a linear quantum universe where copying is hard, where you have to implement copying in some way. Okay, so that's one direction. The other direction, which almost everyone who engaged in providing a semantics or a mathematical model of linear logic went, they started because everybody was trained in set theory. They started and gave an implementation of linear stuff in terms of sets. So you could think of this as like a classical simulation of the quantum world. Does that make sense?
Yes. Yes.
Yeah. So you can either go from set to linear, or you can go from linear to set, and then you can combine the maps, and you can see, how much cruft did I introduce when I went that way. So if I go from set to linear, where I'm introducing all the coding for copying, and then I go from linear to set, right, where I introduce all of the all the set machinery to keep track of all the copies, right? Then you can compare the results of the two, right? how does the set thing compare to the round trip thing, right? So that's also useful and an interesting exercise. Long-winded answer to your question, but hopefully it gives you some context.
And then we can also think about if we have a proof of A and we have something like function from A to B.
Yes.
We cannot expect that if we have two things like A to B and A to C. We cannot assume that we have B and C if we have only one A, right?
That's right. In a linear setting, that's correct. Yes.
Yeah. And is this somehow related to if we want to think about space? That it's not the same if we go from A to B to C directly from A to C.
So there's a connection for sure. There's a connection. You can think about generalized metric spaces, but like in this setting, the triangle inequality is flipped around. So you want it to be the case that the Q value that you get for if I, let's say I take x of x1 x2 and then I tensor that with x of x2 x3, that's going to be less than going from taking x of x1 x3. So that corresponds to composition. So the x2 is kind of hidden inside, right? When we do function composition, where I go from, f of x1 to F from X1 to X2, G from X2 to X3, and then I compose them, G ring F, right? That goes from X1 to X3. And so the X2 part has been hidden inside the composition. And so the Q category, the requirements on Q category are like that, but using tensor as a form of composition. Does that make sense?
Yes, yes.
Okay. So that's why this is really different than sets. It's not sets. Yeah. And you know, like, again, what I'm focusing on is one logical foundation, where, you know, we can have a hope of grounding things out in something that's a little more physical, right? Sets are decidedly non-physical. What the way I used to teach it to my kids was, sets are bags with promises. You can always redeem the promise if you want, but you know, if when I put in when I say I have a set of you know, a red apple and an orange and a yellow lemon, when I open up the bag, I don't actually see those things in the bag. Why? Because I can also put the red apple in a different bag, right? I could put the red apple in a set that has, you know, a red apple and a yellow banana, right? And so how could the apple be in two bags at the same time? Physically, that can't happen, right?
Yeah.
So instead, when you open up the bag, what you see is a little slip of paper that allows you to redeem the paper for the apple. Now, you don't get to, if you redeem that apple, again, that redemption process is not the same as taking it out of the other bag, right? It's still like, if you it gives you viewing rights, so to speak. So you're allowed to zoom in on the apple. Right, but you're not taking it out of the other bag. Does this make sense? Do you understand what I'm saying?
I think so. I think so.
Yeah. So set theory from that perspective is decidedly non-physical. And Q categories, they're not tremendously physical, but they're more physical than sets are.
I'm thinking about this X relation. For the elements of the set, we don't say anything, right? And
I'm not sure what you mean, don't say anything.
I mean, we don't need to express any relation between elements, right? When we say
the elements of the elements of the underlying set, absolute value X, they are related, right? You know, they're related in this way.
Oh, I'm thinking about like in normal set theory, we don't need to say anything.
Oh, in normal sets, yeah, you don't have anything like this. You do have a notion of relationship, right? But not that's, yeah, it's different.
It's like not necessary, right? And so I'm thinking what would be the process of like
no, it is, if you think about it, right? Like, if I give you the integers, you know that part of the structure of the integers is a less than or equal to relationship. It's just that the less than or equal to relationship of the integers comes in only two flavors, true or false.
Oh, I'm thinking I was thinking that for integers we can also say how much they're related, if this makes sense.
You could do that, but then you would leave the normal notion of integers.
Mhm.
So anyway, so the thing is that this is still quite not all the way there. And the reason it's not quite all the way there is that this is Q valued. And what we really want is a notion of comprehension, right? So we want to be able to relate this logic to a notion of comprehension. And there are a few ways to do this, but that's for another time, because we're already close to the top of the hour. But you know, in the, you know, we know how to relate true and false to a comprehension, right? So, you know, if I write down, give me all the x's such that this condition holds, right? So all the x's from S such that a particular condition holds, right? So what you do is you go and evaluate the condition. Given an x, you evaluate the condition, and if it's true, then you throw the x in a bag, right? In your collector, and if it's false, you throw it away, right? So that's you can think of comprehensions as sort of like filters, right? So you could also think of filters on Q categories.
Mhm. And comprehension, you're thinking about some kind of way of maybe defining infinite, something infinite, and not
Well, I mean,
specifying
you know,
directly
like
overalls.
if my comprehension has a stream interpretation, right? So it's boundless. I can still think about, or if my basic data type is stream, I can think about a comprehension as a filter on that stream, right? So it gives me a new stream.
Mhm.
And I can do the same, you know, I can give a filtery Q category kind of thing. Such technical language. But I'm just trying to convey some intuitions here. Okay. I really, unless there are any other questions, we can stop here, and I thank everyone for your time and attention. And I'll see many of you in Dev Stand Up in just a few minutes.
Thanks.
Thank you.